Okay, we got the meeting recording going. I'm starting from our main page. I'm going to click on modules. We're going here through week 4, class information. And I've been adding stuff. I'm running a little bit further behind than I wanted to. I wanted to have weeks 5 and 6 totally done and loaded, and I only have skeletons of those. It's been a very hectic week. What we're looking at right now, just so you folks know, is the large possibility that the district will be, the bulk of our classes will be online for the spring semester. And then we're hoping that we can add some classes that are hands-on classes for like the second 8 weeks, maybe second 5 weeks, third 5 weeks, something like that. The district is deciding to play cautious, and they're not looking to commit to a schedule just yet because they're really nervous how the cold and flu season is going to pan out in our community. So I've been busy in what I will call scheduling hell, coming up with various scheduling scenarios that will have the majority of classes will be online. And then what you're likely to see pop up later in the semester on the schedule is some hands-on classes, but those won't be the earliest ones on the schedule. Okay, so that's what's going on in our program. We're also looking at doing some other things as far as what to schedule online. One of the classes we haven't run in quite a while, or actually one of the certificates within our program, is the parts and service. So we have a service advisor class, we have an automotive parts class. We're putting those into an online format. So you guys going through the program, you could at least get that certificate next semester, the parts and service certificate. So we're excited to get that thing going. And like I said, the hope is that by second 8 weeks through the semester, we'll, you know, a few weeks into the semester, hopefully you'll see those second 8 weeks classes pop up on the schedule. Okay, so that's what's going on within our program. I have one other bit of good news, and that is our work experience class, AT 298, is still going, and you can work in job sites. And what we're looking at is using that class to count for other classes if need be. For example, let's say you were in brakes class last semester, the spring semester, and that class stopped halfway through, right? But you got some brakes training done. What we can do is, what we're working on being able to do is to come up with a list of items. And if you can do those in your shop and maybe get signed off by a mentor technician in the business or something, that we can then do a petition to give you credit for other classes. So we're working on pushing the envelope, because I know several of you are stuck in limbo halfway through the program. And so I want you to know that we're really looking at all of our options to allow you folks to continue to move through the program. All right, with that, speaking of moving through the program, we got to move through this class. This week I added a bunch of links, everything from links on how to use a meter and how to measure current, how to measure volts. And you can see here they have a Fluke 85. I have a Fluke 87 here, and the Fluke 87 and then later the 88 kind of became like the automotive de facto standard. And so I also have a presentation loaded up that I've basically taken my advanced multimeter presentation. I've been breaking it down into little chunks. And so that's in week 4, and it's under Fluke DMM with voltage drop testing. It's really part of a big presentation I have that's 100+ slides, and I'm kind of chunking it down to make it fit a little bit better. So we're going to look at that tonight. And like I said, we're also going to do some live multimeter tests. So with that, what I'm going to do is get a couple things punched up on the screen, and I have to apologize. Remember, I get so many tabs and windows open on the computer at once with Zoom. It's hard to see what you have going on. So I'm opening up that big PowerPoint presentation right now. And I'm going to move the chat back to the side. And I'll change our screen share. There it is. Okay. So, all right. Advanced DMM use. It's all about getting the most from your meter. I got some of this material from CarQuest CTI. When you're done and gone from ARC, when you're moving beyond what we offer at ARC for automotive training, right? You have limited options. If you work for a manufacturer like BMW, GM, Toyota, there's the manufacturer specific training that they provide. But if you work at an independent shop, like I spent a lot of my career at, you're really struggling for training. Well, CarQuest has put a pretty good training program together called CTI. It's not hands-on, but it is a good thing to, they're very up to date on industry trends, and it's a good training, especially for those of us in the aftermarket, if you will. Now, this training focused on the Fluke 88, and like I said a little bit ago, the Fluke 88 kind of became the de facto standard of what all automotive-based multimeters compare themselves to. Our Snap-on 596 meter, the specifications it's trying to achieve, what it's going after is this Fluke. So it's kind of like when you're comparing engine oils, everybody compares their oil to like Mobil 1. Well, that's how it is for meters. It's a lot of manufacturers will compare their meter to the Fluke 88 for automotive use. All right. So with that, like I said, many automotive meters emulate this thing. Your tests are only as accurate as your meter. These are some of the accuracy specs of the Fluke. I'm going to skip through some of this stuff pretty quickly. Like the majority of our meters, that thing has a rotary switch with all the different little symbols. And of course, we know that we have to be able to understand some of these symbols, like that's ohms, and then there's an audible signal right there. This guy can also test capacitors. There's a diode test. So this meter does have some advanced features. It can do temperature, it can do RPM, much like the Snap-on one will. So it's an advanced meter that's in particular made for automotive use, and that's why you see some automotive specific readings on there. Of course, we have volts, AC and DC on there. We have milliamps and amps, and then also microamps. So lots of different things that it can do. All right. On top of that, it has a bunch of push buttons, and these are the things that kind of later on I'll focus on in their class, because they're kind of, you have to have an advanced meter to have them, right? The min-max feature, selecting a range, auto hold is really nice. It can also do frequency and some other things. It has a resolution on it that you can adjust. So those are some of the advanced features. Also temperature. Those are things we'll talk more about at the end of the class, because most of the time, you know what you're going to be doing? You're going to be measuring voltage, and that's what we're going to focus the majority of our time on. The yellow key, a lot of these meters have this where they have this key on the side, and that's the function key. So the idea is that if I touch that key, I can then get the things that are highlighted in yellow. So it allows me to switch from amps AC to DC, to jump into RPM, to jump into a capacitor test. So kind of like a calculator with a function key. It works the same way. It gives you extra features of the meter. All right, and then there is some important stuff here. In fact, some of the stuff my old Fluke 87 here doesn't say this on the leads here at the bottom, but this is important stuff. First of all, the V hole, if you will, that's where you're going to put your volts probe, right? But you can see that it also, that's where you plug in for temperature probe, RPM, diode test, ohms measurement, all happen right there. Of course, our common, our black lead, he just hangs out in that spot there. And then we have our amps and our milliamps and microamps. And old Miss Cheryl, Miss Tushima, she talks about, like, don't leave your meter probe in the old A hole, right? In the amps position, because the danger if you do that is you could accidentally blow up your meter. And I'll show you what I mean by that later tonight. But I also want to point out one other thing. Well, actually, now that I look at this, I want to point out three other things. You know how I am. Notice that this guy is fused. This guy is fused, which is nice. And we're going to be testing those fuses. But also, it talks about these CAT or category ratings. So this meter is rated up to Cat 3 levels to 1,000 volts and to Cat 4 levels up to 600 volts. If you're going to be working on a hybrid vehicle, 9 times out of 10, the specifications they want your meter to have is that Cat 3 rating up to 1,000 volts, okay? My old Fluke 87 does not have that CAT rating on it. And I bet that the meter is built to the standard, but it was before that became a real important thing in automotive use, because this meter's, you know, way older than we had hybrid cars. So that wasn't a big deal back in the 90s, if you will. The snap-on meter, if you looked at it, it has some labeling there that shows you those CAT ratings. So again, I'm going to type this out on our slides here. If you're going to be testing hybrids or EVs and doing high voltage measurements, you're going to want a meter that meets that Cat 3 minimum standard. So I don't want to take my Harbor Freight Tools meter and use it for my hybrid vehicles, right? Okay. So let's clear out those drawings and keep moving. Let's see how well this guy plays. Oh, it didn't play at all. Let's try that again. No, it's not working. Well, what it was going to show was the auto ranging thing, and I'll show you that with a live meter. You get these presentations, they work perfectly, but then when you put the zoom overlay, stuff doesn't always work exactly how you wanted it to. So DC volts, right? It'll let you know that, hey, I'm on DC. There's a little indicator on this meter. And I have here, what produces direct current? Well, batteries, right? And we've already talked about that. Batteries produce DC current, and that's why vehicles, because cars use batteries, I want to be able to walk out to my car the next morning and start it. By nature, we need to have a battery in there, and that means by nature, it's going to be a DC type device. So direct current, that means it's got a polarity, right? And current only flows in one direction. Nearly every system is powered by direct current, right? So we'll clear those scribbles. And so here we're measuring open circuit voltage of our battery, right? with this measurement, I have a question for you guys. Why is it measuring 12.93 volts? What's going on there? What do you guys think? You can yell it out. You can put it on the chat. Isn't a fully charged battery supposed to be 12.6? What do you guys think?
Is it because the alternator, the car is working, this is the alternator charging?
Yeah, you're right. It's the car is not running. If the car was running, we would expect to see, I'm going to say somewhere between 13.8 to 14.8 volts is a good range. This one, the car isn't running. The car is shut off, but it was driven, shut off, the hood was popped, and we measured the voltage. So what you're seeing here is a surface charge, meaning that as this thing was charging, it got a little bit of extra charge on those battery plates. Think of it as there's a few extra electrons hanging out on the plates of the battery, so the voltage looks higher than it would be. And so if you were going to do some battery testing, for instance, and you didn't want this surface charge to impact your results, what you could do is turn your headlights on for somewhere between 15 to maybe 30 seconds or so, and then turn them off. And at that point, you should see that this guy would then drop down to that 12.6. Okay, so that's not an abnormal reading if you just driven the car and then you shut it off and pop the hood and measured the battery voltage. Good deal. All right, moving right along. I think one thing that's important to remember is, what is the voltmeter really doing? Well, it's just measuring the difference in voltage, right? The difference in potential, electrical pressure between 2 points, wherever those 2 voltmeter leads happen to be. It's just measuring the difference in pressure between these 2 leads, right? So normally we would put black to the negative battery post or the most negative part of the circuit, and red would be going to the most positive. But it's up to you to figure out, where do I want to put these leads, right? Okay, so if I keep this going, because we already looked at that open circuit voltage, right? And we talked about the surface charge on there. Remember that 12.6 is considered 100%. Batteries, and I guess I should say specifically what we're looking at with this table is a chart of lead acid batteries, right? Because these days with hybrid vehicles, we have nickel metal hydride, we have electric vehicles with lithium ion, we got multiple different types of battery chemistries now, right? So lead acid batteries, your typical batteries that have been in cars for a bunch of years, fully charged, they should have 12.6 volts, right? But, and how do we get that? Well, there's 6 cells, and it's 2.1 volts per cell. And you do the math on that, that's how you get 12.6. So one thing you'll notice is that this chart is not linear. Like if I made a graph here, this guy is not linear. It's not just a 1-to-1. So you would think, okay, if I rounded it down and I said 12 volts was fully charged at 100%, then 6 volts would be 50% charged, right? If it was a linear deal. But you'll notice that it is definitely not linear, because by the time I drop down to 12 volts, right? We always call it a 12-volt battery, but if I drop down to 12 volts, heck, I'm only sitting at, just over a 20% state of charge. In fact, 50% state of charge is about 12.3 volts. So it is not a linear scale. It's one of these scales that is very much curved like this, where a little difference in voltage means a big difference in battery charge level. All right, so let's clear that out of there and got that kind of little side note on batteries. All right, so every multimeter has one or more ranges, right? Better meters like the Fluke here or our Snap-on, they're auto ranging. You can put it in auto range mode, and the auto range mode will automatically select which range you want. Now it takes a few seconds for it to figure it out, but the meter turns on, it measures things, and it goes, oh, okay, I'm only measuring 6 volts. I'm going to go down there. I'm testing a charging system. Maybe I'm going to go right there. Or maybe I'm working on a hybrid or working on a house or something. Maybe I'm going to auto range to that. So nice meters have the ability to auto range. Cheaper meters, like our little Harbor Freights and other things, they don't have the ability to auto range. So it's up to us, the technician, to select what range we want. And I did warn you about that last week. You could select the wrong range and you think there's no voltage there, when really it's OL because it's measuring outside of your range, out of limits. So here we are on the 6-volt scale. Here we are on the 60-volt scale. And so you see how it automatically moved the decimal point and how many numbers I had behind the decimal point, right? There it is again on the 600-volt scale. 1,000-volt. So you see, you start to lose some accuracy. What range would I want? I want the lowest range I can get away with for the signal being measured, because that's going to give me the most accuracy. If I back up here, right? If I put it on a 1,000-volt scale, it only looked like it was 2 volts. But when I was on the proper scale, I realized, hey, it's just over 2.3 volts. So if that level of accuracy is important, you want to make sure you select the lowest range you can to get good readings. You could always start off on the higher range and then one by one, click your way down to get to the right range. Okay, so pay attention to the scale or range of the display, right? Because it will give you some readings on there, like kV is for kilovolts on the meter screen. MV is for millivolts. So you can kind of see how the decimal point changes on that. So here we got the same value. This one over here is measuring it in just volts. And notice we've taken it off of auto range. So if I click that, I can put it on auto range. It's no longer on auto range, it's on manual range. So there I've selected 6 volts. Here I've selected 600 millivolts, and you can see how you have more accuracy when you select the smaller range, okay? What I want to stress to you guys one more time is just that on a cheaper meter like this, you really have to pay attention because there's no auto range. So you have to select the right range in order to get good readings. All right. So moving right along, we'll see if this one, no, my videos don't play. All right. So let's jump into some voltage drop testing. Why? Because voltage drop testing is by far absolutely the most common measurement that you'll do. And so what's great about that is I can do voltage drop testing all day long with the inexpensive meter. So with that being said, again, what is this meter displaying? This is open circuit voltage, right? And again, we see a little bit of a surface charge on this guy. Okay, well, what is a voltage drop? It's the difference in voltage between 2 points, but the key here is, and I'm gonna highlight this, even though it's already bolded, is when current is flowing. And so what I like about voltage drop testing is it's a live test. So voltage drop test is done live. meaning that we have current flowing. You can get thrown astray when you're not doing live testing. And I'll show you what I mean here in a minute. So another way to look at voltage drop is that it is describing what happens to the source voltage when it goes through resistance, when current is flowing. So another way to say that would then be voltage drop, change that, voltage drop, it equals resistance. Sometimes we'll call voltage drop and we'll just say VD for voltage drop. So VD, what does that equal? It equals resistance. But again, it only works when current is flowing, okay? If current is not flowing, that can kick you in the butt, okay? Now, voltage drop could be intended or it could be unintended. So let's explain what we mean by that. So let's say this car, it's got the headlights on in this situation. So, you know, current's flowing through it. If I have these leads right next to each other, what is it displaying? Well, it says 0 volts. It's displaying 0 amounts of resistance, basically, right? Because voltage drop equals resistance. There's no voltage being dropped between where the tip of the red lead is and the tip of the black lead. So there's no voltage drop between those 2 points right there. All right. We'll zoom in on that, right? So they're both on the same terminal. So I would expect that. Okay. What's the significance? Again, there's no resistance between the 2 points where that meter, those meter leads are connected. Now, let's say we're doing this again. In fact, this time, let's say we're actually cranking over the car. So that means that I have power flowing out of the battery, going through the starter motor of the car and coming back, right? We're cranking over the car. And current, so we know current is flowing, the engine's cranking over, and I see 0.0 volts. What's the significance of that? Again, what is it telling us? What do you guys think? You can type it in the chat. You can do a shout out. There's little things where you can raise your hand on the Zoom call. There's little features of that. I don't know if you guys have played around with that. I'm gonna type something up on the screen while you guys are thinking about it. Okay, so here is what I was looking for, is that because I'm cranking over the car and the meter reads 0.00, it tells me that I have no resistance in this battery cable connection here, okay? If this cable connection were to be all corroded, so let me draw some, I don't know, some green in here. There was a bunch of corrosion in here. Maybe I couldn't see it from the outside, but there was corrosion on the inside. If that would create resistance there, that resistance would be shown with a voltage drop reading on my meter, okay? All right. We'll do more of these so it'll come together here. Okay, again, we're cranking over the car. So I'm gonna type that up on the screen. Engine is cranking. So engine's cranking. I'm measuring 0.06 volts. So what's the significance here? What's going on? What does this indicate? There is a little bit of what here?
There's a resistance.
Yeah, there's a little tiny bit of resistance. So a little bit of resistance there. Now, it's up to us to determine if this little bit of resistance is acceptable or not acceptable. Since the engine is cranking, and the engine was cranking pretty fast and smoothly, I would say, hey, that's pretty acceptable. Plus, it's not dropping a lot of voltage. Over time, you realize that there's some standard kind of rules for how much voltage you can drop in a circuit. It does kind of depend on what circuit you're testing. In that circuits where there's more amps flowing through the conductors, a lot of those you can get away with dropping a little bit more voltage. But circuits like computer circuits, I really don't want to drop much voltage at all. And I shouldn't, because there's not much current flowing through those circuits. So if it was a computer circuit, I may not want to drop more than a half a volt on the power side and maybe a tenth of a volt on the ground side. On this cable, if I was cranking over the engine, maybe I could withstand a little bit more voltage drop, a 0.7 or a 0.8 volts. You have to kind of ask yourself, well, how much current do I think is flowing through the circuit? And then how's the thing behaving, right? If I was concerned that it was dropping too much, and remember, if I said it's dropping a half a volt, what the meter would say on the screen is it would say, if I type this over the screen, it'd say 0.5, right? That's a half a volt. So this is 0.06. I mean, it's like next to nothing, right? So 0.5 volts, that's also another way to say 0.5 volts would be 500 millivolts. Okay. So what we have on this screen is basically 60 millivolts or 0.06 volts. So that's looking just fine. The car cranked over nice and smooth here, so it wasn't very exciting. But the idea is that if you see a reading on your meter, that tells you that there is a little bit of resistance there. Okay. Now let's say this thing didn't crank, like I went to go start it and it went click, 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 and it would not crank over. Click. And then I went to measure my voltage here, and what my meter said on the screen here is it said, it said 5.5 volts. Well, I would go, oh my goodness, that's a ton of resistance right there. No wonder it's not going to crank over. This guy is indicating that there is a lot of resistance right there. Okay, so that lot of resistance is going to reduce the current flow. I've drawn these before, but I think I'm going to draw it one more time here. Remember, volts, amps, and ohms. What Ohm's law tells you is that, hey, I got the same 12 volts in my battery, let's say. If the resistance goes up, which it would indicate a lot of resistance if it was dropping 5 volts, that means the current flow is going to go way down. And I can't stress this enough. Remember, it's the current that does the work. So why does the engine not crank over? I can't get adequate current flow through the components, through the starter motor to crank over the engine. All right. So here's a better shot of that kind of zoomed in, how they're testing it. So we didn't have resistance. We didn't have resistance between this point and this point here, but we have a little bit right there. So that means I might have just a slight bit of resistance where it connects there, or maybe where this cable connects to the copper wires. All right. A question that came up in one of my other classes that honestly, for several years, I didn't quite understand it was like, look at this connection right here. In electrical class, right? And I know a lot of you guys have taken the electrical class. We talk about, we like to have nice soldered connections. That makes a great electrical connection, and it does. But oftentimes you'll see manufacturers and they'll have a cable connection like this one right here, and it's not soldered, right? There's no solder on that copper wire. You go, what the heck's going on? Why don't they solder that? We're seeing more and more where they do not solder, they just crimp. They might put some weatherproofing around it, but a lot of times they'll make crimps and they'll seal the crimps without solder. The downsides of solder is that if you've ever soldered some wires, it wicks up the lines and you lose some flexibility of the wires. It also costs money to add solder. And so more often than not, you'll see crimps on harnesses that are not soldered. Even in motorsports, and a lot of you guys that know me know I'm a big motorsports guy. When we're putting together like a mil-spec wiring harness, there's very few, if any, solder joints in that harness, because in racing, they want everything to be super flexible for vibration. So it's all tight crimps and weather pack seals, not a lot of solder joints. I'm getting sidetracked, but looking at that image, it kind of reminded me of that. So, all right, moving right on. So remember I said that there's intended voltage drops and unintended voltage drops. This would be a great example of an intended voltage drop, because if we look at the current flow in this circuit, right, we're going to think conventional current flow theory, and so power would come from the battery, go through the blower fuse. If we select our fan speed switch to low, it has to go through the blower resistor, right? And the blower resistor is going to create a voltage drop. It's intended resistance, so it does just what we want it to do. It creates a voltage drop, right? Meaning that the resistance or ohms increases, and that means the amps is going to decrease, and ultimately, when this current flows through here and ends up going through the relay, and I'll get to the relay in a minute, and then flows through the motor to ground, there's going to be less current flowing through that circuit. And in this case, that means that our fan is going to be turning a little bit more slowly, right? That's how we control the speed of the fan in this type of circuit. Of course, I can then select a different position. Maybe I want it to medium 2, so I come up to 3 here. And what you'll see is I'm bypassing a lot of that resistance. So that means the resistance is going to go down, current flow is going to go up, and the fan is now going to be spinning faster, right? Okay, one other thing to point out here is in this circuit, we have a relay in line here with the circuit that basically controls what's going to happen with this fan. And we're going to spend a little bit of time talking about relays in just a minute. All right, so let's clear out some of these drawings. I just got to get to unintended voltage drop. That's a voltage drop. We didn't engineer it to be there, right? It could be resistance across a wire. It could be a bad switch. It could be a high resistance relay. I have voltage drop. Remember, voltage drop means resistance. I have resistance, voltage drop, where I don't want it to be, okay? So again, if I measure voltage drop and current's flowing, that means resistance is present. And then the key for us as technicians is we got to determine, well, is this an excessive amount of resistance or is this acceptable, right? excessive resistance is going to mess up that circuit. It's going to negatively affect that circuit. All right. Now these unintended voltage drops, they can happen in the power side. Oops. They can happen in the power side, or they can happen in the ground side of any electrical circuit that we happen to be working on. Okay. So how much resistance in a circuit connection is too much? So we have 0.1 ohms, 0.01 ohms, 10 ohms, 100 ohms. What do you guys think? How much resistance here is too much? Well, I won't leave you hanging forever. The answer here is that it depends. Depends on the circuit. Depends on how many amps are flowing through there, what the circuit's trying to do. It really depends. And keep in mind that we're usually going to be measuring this resistance through measuring voltage drop, not by measuring current flow. And then that brings us to the question as to why use voltage drop versus ohms? And for that, we're going to fire up the document camera. So what I'm going to do is I'm going to clear out my scribbles. I'm going to exit out of this thing. I'm going to close that out. And we've stopped screen sharing for the moment. But that is okay, because what we're going to do is we're going to change that screen share just to my desktop here. And I'm going to minimize myself and get some stuff out of the way. All right, now let's see, where did that go? There it goes. I have a couple of meters over here that we're going to fire up and do some testing on my workbench. So we'll get this guy set to that. There we go. Get some meters going. Okay, there's a little bit of a reflection here, but not real bad. Okay, now you can see, man, I have all kinds of stuff up on this desktop. But we'll clear some stuff out of here, out of our way. All right, we'll start with the cheap meters. I'll work our way from there. So a few of my questions were, why don't we measure resistance just by using ohms? Okay, we can certainly do ohms testing. In fact, to do some ohms testing, I'm going to get this guy out of the way. Use this little black one up here, and I'm going to set it to the 200 ohm range, right? And I have a relay right here. I want to test the control circuit of that relay. Now this week, I did put up some information on relays. This guy's measuring that the control coil in the relay has 73.4 ohms. Let me switch this back to my computer screen real quick. And my mouse. And can you guys see that picture of that relay on my computer screen? You can give me a thumbs up or a yes or no on the chat. Because what I want to do is now switch it to this diagram here. This is your typical DIN, or a lot of times I'll call it a Bosch relay. This was standardized in the late 70s, very early 80s of the different terminal configuration here. where if I look at the bottom of the relay, it's got terminals 86, 85, 87, and 30. And if I look at how this thing is wired up, what I would see is on the inside of this, if I put my drawing tool back up here, we'll go with blue, I guess, is that there's a coil of wire that connects 86 to 85, and these are our control circuit. That would go to our switch typically. And then a magic thing happens when I flow electricity through a coil of wire. It makes a magnetic field, right? This thing that looks like a circular football here now is my magnetic field. That magnetic field generates as current flows through there from 85 to 86. And what that causes, what that magnetic field will cause, is a set of contact points to close between terminals 87 and 30. So the relay turns on, the contact points close when I flow current from the control side. The 87 to 30, that's my switch circuit there. So that's how that relay works. It's an electromechanical device that uses magnetism to physically close contact points on the inside, right? Why do we put a relay in a circuit? Well, the relay protects that circuit so we're not burning up switches and other things. A computer driver can't flow a lot of current. So I'm gonna have that computer driver control a relay. The relay can handle a substantial amount of current, so that protects my computer from flowing all that current. Now, there's a couple of other connections in here, namely that terminal 87, this one in the middle is actually 87A. This is always, these guys are connected together. When the relay turns on and the magnetism generates, it then disconnects from 87A and then jumps down here to 30. Okay, so that's how that's wired up on the inside. Now I can test out that wiring by looking at my actual meter on my document camera. So let's get that guy back up. So here I'm going between terminals 85 and 86, and I can see the coil of wire in there, my control circuit, has a resistance value of 73.3 ohms. It's a great little bench test of a component. If I went between terminals, I'll keep it in the same orientation, 87 and 87A, you can see that I have next to no resistance, right? Those two are connected together. And of course, right now, if I went from 87 to 30, the relay's all, not turned on. So right now that circuit is open, right? Okay, so to test the relay out, what I'm gonna do is I'm just gonna use a little 9-volt battery. Why? Because 9 volts is close enough to make this relay work. So I got a couple little jumper wires here. I'm going to put one lead on there, and the other lead I'm going to put on the other side. And when I do that, you'll hear the relay click. And when the relay clicked, you can see that now I have continuity between 87 and 30. So this is a good relay. I no longer have continuity between those two, right? So I did a little bench test with my ohm meter on that relay. So anyways, we've tested out the relay. It kind of shows you how, like, when you're doing ohms testing, you're really doing kind of bench test work here, right? So typically when I'm measuring ohms, there's two key phrases here. The circuit is off and it's isolated. in that this thing's totally isolated. It's not plugged into a car. There's no extraneous wiring here. I'm just testing that component. And the power for my ohms test is, you know, coming out this lead and coming back in this lead. So when I'm testing ohms, my meter is the power source, and that's why the circuit needs to be off and isolated. So how can I show you that the meter is the power source? Well, I'm going to take this other meter. I'm going to turn him on. It's a little different setup, and I know this is a 9-volt battery. I'll just measure how many volts it has real quick so you can see that the meter does work. All right, it's sitting at 9.5 volts. All right. So how much voltage is the meter actually putting out on an ohms test? It's putting out 3 volts. Okay, so that's how much voltage the meter impresses on the circuit to measure volts. Okay, so I said ohms testing is good for bench tests, but it's not a live test. And so remember, the question was, why do I want to use voltage drop testing to find resistance rather than ohms testing? Because, heck, this meter's only putting out 3 volts. And I'll show you a couple other things here. I'm going to lay out a couple pieces of wire. There's a cable I'm putting together for the Formula V. It's going to go to the starting circuit. And then here's this other little jumper wire we used. Which wire would you rather use to try to start your car with? And that, which wire would you rather be going from the positive battery to your starter motor? This little one or the big one? Go ahead and yell out a response, or you can, you can tell me on the chat.
Is the big one? Is the big one is good?
The big one, right? I don't want everybody like, hey, that's pretty easy. I know I want the big one, but here's what's weird, okay? I have this meter set to ohms, remember, and I'll put the 2 leads together and see what the resistance is of my leads. Looks like my leads have 0.6 ohms, 0.5 ohms in the leads, okay? So now I'm doing a resistance test.
Oh, got you.
Of this wire, and it comes out 0.5, 0.6. Okay, it comes out very low, right? Which is what I would expect. This is a pretty good size piece of cable. I've done a great job putting the ends on there. That's what I would expect on this. But conversely, I'm going to test this little jumper wire here. I can get my alligator clips to clip on the little alligator clips. And again, I measure almost, the same exact 0.5 ohms. So according to the ohm meter, there's no difference in those 2 cables. But we know absolutely there is a difference, and we know which one we rather start our car with, right? Or which one would actually allow our car to start and which one wouldn't. This one, if we tried to start our car with it, it'd actually just burn up the whole wire. So many amps try to flow through it, it just burned it up. The difference is remember, when the meter is set to measure ohms, this meter only put out 3 volts of electrical pressure through the circuit and even less current. Now, how can I test that? Again, I will connect one meter to another meter. So I have this meter, it's still set to measure ohms. All right, it's still, oops, we'll minimize that. It's still set to measure ohms. We're gonna take the Harbor Freight meter. We're gonna set that guy to measure amps. It's a brand new meter, so unless somebody got in here, the fuse shouldn't be blown on this guy. I'm gonna prop it up so there's not so much reflection on the meter. Okay, and if I take off my alligator clips and I come in here, I'll try to make a connection here. Okay, so it's saying this is what is going on. This meter can't even measure how many amps it's putting out right now on the 5 amp scale. I'm going to have to go to the milliamp scale down here. I crop it up again. You'll see right here it says milliamps. So I'm going to go down to a 200 milliamp scale. And I'm going to try this again. Oh, there we go. Gosh, there's not a lot there. Let me go down to 20 milliamps. There we go. So when I do that, you can see that this number changed because it got a little bit more accuracy. So on the 20 milliamp scale, what it is reading is that this meter, we know it's putting out 3 volts because we already tested that. And it's applying 3 volts and it's flowing 1.88 milliamps. That is how much current is flowing out of there. And this meter here, remember he set the ohms, so he's saying that the resistance of this meter is 13.6 ohms, by the way, 13.5 ohms. So here's what I'm trying to get to, guys. The reason this cable tests out to the same resistance value as that cable is that meters, when they're set to ohms, they're applying very little voltage and they have very little current flowing through the circuit. And I'm not going to detect a problem. In fact, I'm not even going to detect a difference in the resistance of these 2 cables at only 1.88 milliamps. With that little bit of current flowing, those cables test the same, right? So the reason we do voltage drop testing is we want to have live testing as much as possible, meaning that we want realistic amounts of current flowing through the circuit. Even if that circuit doesn't operate correctly, I try to make it operate and I'll measure that voltage drop. Now, you might be saying, okay, now wait a minute. You're trying to fake me out. You're trying to fake me out. So what if I didn't use these real cheap meters? I bring out the big dogs, so to speak. I'm gonna bring out my Fluke meter, and I'm gonna bring out the snap-on. Okay, let's see, that one set to ohms. I will set this guy to amps. All right, so he's set to amps, he's set to ohms, and I gotta get us some leads going here. And of course I got leads and stuff all over the place. So that is not the lead that I wanted. Oh, here they are. I like these Fluke leads. They kind of plug right into stuff. So okay, ohms, and this guy's going to go to amps, and this guy's saying, hey, this meter has, oops, I went away to, so he's reading that this snap-on meter has a resistance of 0.2 ohms, and the snap-on saying, hey, you're flowing out, you know, a 0.5 milliamp. In fact, let's go down to the milliamp scale. So I'm going to move this guy over, and we get a little bit better resolution. So this Fluke meter, right? That meter, it's at least a $500 meter, and we know the snap-on's like $700 or something. So the really good meters, same readings I had before though with the cheapies, is that when I'm set to measure ohms, I'm only pumping out, so to speak, 314 milliamps, or actually 314 milliamps. So 314 microamps. So next to no current is flowing out of the meter. Now, if I wanted to see, well, how many ohms or how many volts is coming out. Well, remember that the little Harbor Freight meter, it was pumping out 3 volts. This Fluke meter is only pumping out 0.6 volts. So again, I don't care what quality of meter you have, you're going to miss potential problems on an ohms test because you're just not applying enough voltage and getting enough current flow to go through the components oftentimes to detect those problems, okay? So oftentimes we'll call an ohms test a continuity test. All right. Now, I see that at 7:30. You guys know how I like to always end on a tech tip. And my tech tip tonight is to always test your tester. So that starts by reading your instruction manual and being familiar with that, right? What I'm going to show you is right inside the manual, so it's not necessarily hidden information, but if I want to know if the fuses are good in my meter, I can do a quick continuity check. I'm going to do it first with my snap-on meter. I'm going to hit this function key, and it turned on the little symbol that looks like a speaker because it's going to make an audible beep if I put these leads in the meter and I were to touch them together, if I can make that work. You'll hear that noise. Okay, so I know the leads and stuff have continuity. And if I want to test my fuses built into my meter, I just got to plug it in. So that fused 10 amp circuit is good. This fused 500 milliamp circuit does not appear to be good in this meter. Well, wait a minute. I better make sure that I'm not on some type of weird range or something. So what I'm going to do here is I shut it off, turned it back on to put it in auto range mode. And what I can see is it does have continuity. So the fuse is actually okay. It just has a lot more resistance in the meter on that scale, okay? And that's normal. How would you know, especially what it's supposed to read? You can read your owner's manual. But if it doesn't say out of limits, it's okay. Now let's do that same test. Let's do it on our snap-on. So I'll get the, or I'm sorry, let's do it on our Fluke. We just did the snap-on, didn't we? So he is set to ohms. I'm going to plug the leads in. We know we've already tested these leads and the leads are good. So with that, I'm going to test that fused circuit, and it says 0.2, 0.1 ohms. It also gives us that audible chirp. I know that fuse is okay. Let's test this one. I got nothing. Okay, well, wait a minute. Maybe I got some type of weird range thing going on. I'll turn it back off. I'll turn it on. Now it still says OL. Heck, I'll even put it on diode test. Nope, nothing. So what that's indicating to us is that that fuse is bad. Inside our meters are these special types of fuses. They're not like regular automotive fuses. They're fast acting and they cost about 10 bucks a piece. I've already unscrewed this meter to make this go a little quicker. Take off the rubber boot. There's 3 screws there. I've taken those screws out and we'll crack this meter open. And of course, you know, being an automotive meter, they try to make these water resistant. So that cover has a gasket. It fits pretty tightly. I can change my battery. Here are my fuses. Now, remember, one of those fuses didn't test out. I'm going to do something sacrilegious here. I'm going to use a less than $10 meter to like this is I think I paid $7 for this. I'm going to have the $7 meter test the fuses of a $700 meter. Okay. This is my 10 amp fuse. You can see the resistance is very low. This is the milliamp fuse, and you can see that that one is out of limits. If I take another one of these fuses, one thing you'll notice, I don't know if I can get this to zoom in or not. I will try. It's kind of hard to read these fuses. You're like, what am I even looking at here? Let me focus that thing. Do you see how scratched into the barrel here it says 440? That's 440 milliamps. That's what that fuse is set to, right? So DMM, that's the 440. That's the little fuse, if you will. So what we would need to do is pop that little fuse out of there. And pop this guy in there. Get him centered up. Now, I'm going to drop my case back on. I'm not even going to worry about the plastic boot or anything at this point, so I can do this pretty quickly. I am going to set him back to ohms, and I'm going to do that resistance test here. And remember, how do I do that? Well, I take my lead, and really I don't even need the negative lead. I just need the positive lead. I plug that lead in, and the other end of it, I'm going to plug into my different A-holes, if you will, or amps selection. So that one measures out, it's beeping. You can see it's got a very low resistance value. This is not going to have as low of a resistance value. In fact, it measures 1,000 ohms, but it's beeping, and I have a reading on my screen. If I read through my manual here, remember this procedure is actually inside, and it tells me that's a normal reading. So always test your tester. One of the most common things to happen to a multimeter is that it gets the fuse gets blown on there. And so with the fuse getting blown, you will not get good amps measurements. Next week, we'll get into more of how the fuse gets blown and kind of lead you down that. But we did some component testing tonight with testing the relay. We also tested the meters, and I showed you why we use voltage drop to measure for resistance. And we talked a little bit more about voltage drops and how the meters work. Next week, we'll continue on. We'll get into amps measurements and voltage drop testing with some circuits that I build here up on my desktop here. I also am working on some other video clip series to add to your website as well. Okay, so that's the bulk of my content for you guys tonight. I did have one other thing come up, so I'm going to change my screen share. Here we go. All right, and I'll go back to the internet, and that is I got a email question on the chat here, and so the email question, it wasn't under our discussions page. It wasn't under the tech help, but I was emailed the question for a starting circuit on a 2002 Chevy Express. So let me put that up on the screen. So this is, we're kind of in bonus time, if you will, here. So what's the deal with this starting circuit? What I've done is I put in the vehicle 2002 Chevy Express. I guessed that it was the 5-liter. The cranking circuits are the same, pretty much wiring for all of these. Remember, what I like about ShopKey Pro is they redraw all the wiring diagrams. So that makes things a little bit nicer, a little bit more consistent to read. And we're going to just start going through and highlighting stuff so we can see that we have power going through here to an underhood relay center. If it's a diesel as an auxiliary battery, let's start to highlight some things here. So what I'm going to do is I'm going to highlight that because power would go through here, and it either would have another battery in parallel if it was a diesel, or it wouldn't have it if it was gas. It would just go straight from here to there. Power would go from the positive battery post through the fusible link. And one thing you'll notice about wiring diagrams, how they draw these wiring diagrams is, if I can get my annotation tool. I don't want that. I want to this. If I can get my annotation tool up on the screen. Is that you'll start with power typically at the top. You'll have your circuit throughout the page. I don't know what that is. That's my circuit, that squiggly line. But ultimately, you're going to have your ground at the bottom. Most circuits are drawn so that there's this linear from top to bottom power flow. Now, I know on this circuit, it's kind of coming from the side, but still it ends up at the top, and then it flows down to the bottom of the page. So that's usually how these drawings are made. Okay, so I've highlighted all these wires, and by highlighting them, what I'm saying is that at these spots, I would expect to have 12 volts here, and it doesn't matter if the key is on or off. I should also have 12 volts there, right? And we know if the battery is fully charged, it'd be 12.6 volts, right? If this thing didn't crank over, well, there's likely a couple things going on. So I gotta scroll down here and see, well, if I turn the key, let me clear these drawings. If I turn the key to crank, what's supposed to happen? Well, power goes through here. I turn it to crank or to start. It goes through that fuse. If I look through here, it's got to go through the park neutral switch. I'll redraw that. So if I'm in park or neutral, it goes through there and it goes back up to the starter relay. One thing you'll find different between a more modern car and an older car, and I wish I could get this whole thing to fit on my screen. I guess I could zoom out one level. Of course, now my scribbles don't quite fit, but one thing you'll notice is that an older car, it would go from here and it would have gone straight to the starter solenoid. Newer cars typically will include an extra relay. They call it the starter relay. And that relay can look, well, I got a big mess here, but they can look identical to this relay right here. Nothing special, but it goes through that additional relay. So that comes in, that controls the windings of the relay. When the relay turns on, then the relay contacts click, and that's what sends power down to the S terminal. Why do they do that? because they're trying to minimize how much current has to flow through the ignition switch. If you've ever tested one of these starters, it's not uncommon to have 10 to 20 amps flowing through the starter solenoid with a peak current draw of 40 or more. So to limit, to not have to flow all those amps through the ignition switch, they've incorporated that relay. So if this engine did not crank over, a place I would look right away is I would jump to that starter relay. Why? Because it's going to be relatively easy to get to because we know it's in the underhood fuse relay center. So I'd find this relay and I'd say, all right, well, if it's an ISO or a Bosch style relay like this, I can just take relays out and switch them, right? So maybe there's a fog light system with the fog light relay and I turn the fog lights on, they work. I know that relay's good. I'll just switch it and I'll see, does it crank over now? If it does, then I know I have a defective relay, right? So don't overlook what I call plug and play diagnostics. So you have that relay in play. Ultimately, if the relay's working, right, I should get 12 volts or very close to 12 volts here. With all this mess that it's going through, the relay and everything, you know, maybe I could withstand maybe about a 0.7, 0.8 voltage drop here, but I would expect to have something close to 12 volts here, and I would expect to have something close to 12 volts there. And if I have 12 volts at this location and 12 volts at that location, when I have my fingers on the key and I'm trying to crank it over, well, that tells me that, you know, this circuit's doing its job, the relay's energizing and he's doing its job. And if I have 12 volts here, well, then my problem has to be on the other side of this thing, right? It has to be on the other side, which it could be, maybe I got a defective ground. That's not very likely, but I have seen vehicles where like somebody just did a transmission job and now the car intermittently doesn't start because the starter bolts are loose. They didn't tighten them down all the way. High resistance at this ground connection right here. So that's a possibility. More than likely, it would mean that I have a resistance issue in the starter. If it didn't crank over, but I had 12 volts at both of those locations. So that's a little bit how you would pick apart the wiring diagram. And it's kind of like you look at the diagram and you think in your mind, okay, this is what I expect to measure here. So if I thought this out and I walked over to the car, and again, you can see how if I'm doing these tests on the car, having these alligator clips where I can clip my meter onto where I want and then jump back in the car and crank it over are really important. So that's why I said that was one of my tech tips from a few weeks ago, is get those alligator clips. But what that means is that I would expect to have 12 volts with my finger on the key at that guy right there. And I would expect to have 12 volts right there. So if I go and I did my voltage measurements and I took my meter, I think to keep it, to go with our theme of oh, that was supposed to be yellow. To go with our theme of a Fluke meter, I'm gonna draw it yellow and black here. If I were to take my leads and I took the red lead and I went right here, and I took the black lead, and the black lead, I just went to ground. I went to the negative battery post or whatever. I would expect to see 12 volts there, and I would also expect to see 12 volts right there. And if I didn't, then I'd start working my way backwards to figure out, well, where am I losing it? Now, obviously, step one, measure your battery open circuit voltage. Make sure the battery's not dead, right? Don't overlook that. So make sure I got a good charged battery. So if I'm assuming my battery's good, I start feeding through here. I got my finger to crank on the key. I expect to measure 12 volts at both of those spots. If I then took my lead, oops, I took my lead. Let's try that again. I took that positive lead, and I now hooked it to the case of the starter, right? Because that's how it gets its ground. And I took this negative lead, and I went over here to the negative terminal directly to the battery. You know, I would expect at that spot to measure 0 volts or something very, very low, a very low amount of voltage drop. Really, I would expect to measure 0.1 volts or less there, okay? And of course, if I measured 12 volts across the ground, I know I have a high resistance ground circuit. So again, you use your meter in combination with your diagram to kind of think things through, figure out how the circuit works, and then you know what voltage to expect there at those different points when you do your measurements, okay? So I think that question was for Tom. Hopefully that answered your question. I'm gonna look here on the chat real quick and see if yeah, no comments on the chat. So with that, guys, I am going to stop the screen share. And I will let you get back to your real lives and get back on your night. Again, I will put the recording up to share it with you folks so you guys can review that, that information. Next week, we'll continue on with more meter testing. We'll do some tests with some series circuits, and we're also going to jump into some more advanced charging and starting system tests. Again, if you have questions, actually, I need to do one more screen share, and that is if you have questions, remember that I have this tech help section of the discussion page that I can answer the question on the tech help thing. I can even post a video on tech help there too, because as you can see, it's hard for me to answer all the questions in our live session and keep it in a timely manner. And I know for a fact that it's hard to keep your eyes straight watching a Zoom for more than an hour. So I really want to try to keep these down to an hour. Okay, with that, it's been great hanging out with you guys. Thank you for being here this evening. I hope you got something from this lecture, and I hope to see you guys back next week. Take care, everybody.
Good night.
Good night.